Okay, welcome back to the class on mechanics of materials. And last time we were discussing very important topic, that was the concept of combined loading. We have to discuss those structural elements or the machine components which are subjected to more than one loading condition at one instant of time. We have already discussed the conditions when a machine element is subjected to actual load only, when a machine element is subjected to torsion only, to bending only, to shear only. But there are machine elements which are subjected to more than one loading condition uh, simultaneously. We have more than one load acting on the machine element. So at that time, we say the machine element is under the influence of combined loading. Okay? So before we can understand the concept of combined loading, it was very important for us to understand what we call as the pressure vessels. Okay, in the previous class, we talked about the pressure vessels and we understood as far as the pressure vessels are concerned, the pressure vessels are the vessels. They are the containers which are used for containing the which are used for containing the pressurized fluids. For example, the pressure vessels are used for transportation of fuel. They are used for the transportation of water. They are used for the transportation of milk, so on and so forth. So their applications are widespread. And we usually see a pressure vessel, uh, on in a local mechanic shop in the form of what you call as a compressor. Okay, the compressor is simply a pressure vessel which is used to contain the pressurized fluid, mainly the air. So that's why they are called pressurized vessels. And we know these pressure vessels are of two types: the cylindrical pressure vessels and the spherical pressure vessels. Then we talked about these thin-walled pressure vessels. I said that pressure vessels are of two types: thin-walled and thick-walled. As far as the thin-walled pressure vessels are concerned, the thin-walled pressure vessels are those pressure vessels in which the ratio radius to the thickness of the pressure vessel is greater than or equal to 10. That's what we call as this is the pressure vessel whose R by T ratio is greater than or equal to 10. That pressure vessel is called the thin-walled pressure vessel. Now, after that, we started doing the analysis of the pressure vessels, and we did the analysis of what we call as the cylindrical pressure vessels. Look, as far as the cylindrical pressure vessels are concerned, cylindrical pressure vessels are in the form of a cylinder. Now, within these cylindrical pressure vessels, we have the pressurized fluid. Okay, so within this uh, within this cylindrical pressure vessel, we usually have the pressurized fluid. So when you are filling this entire cylindrical pressure vessel with a pressurized fluid, that pressurized fluid will try to do two things. Okay, that will try to cause the enlargement of the radius of this pressure vessel. That is, it will try to increase the radius of the pressure vessel. If initially the radius of the pressure vessel was r, as you fill it with a pressurized fluid, its radius will slightly change to r prime, such that r prime will be greater than r. Okay, so this is the tendency of the pressurized fluid to increase the radius, number one. Number two is the pressurized fluid will try to cause the increase in the length. Okay, so if initially the length was L, as you are filling it with pressurized fluid, its final length will become L prime. Okay, so this is the pressurized fluid has two tendencies. It has tendency to increase the length of the pressure vessel. At the same time, it has tendency to increase the diameter or the radius of the pressure vessel. The example of it is like you already know that when you inflate a balloon, when you fill a balloon with air, initially the size of the balloon is very small. You can hide it in your hand. It's very small. You can hide the balloon in your hand. But once you are bringing this balloon close to your mouth and you are filling it with air and you are trying to inflate it, as far as the diameter of the balloon is concerned, the diameter of the balloon increases, the length of the balloon also increases. Okay, so there are two effects of the pressurized fluid. The pressurized fluid tends to cause the increase in the length of the balloon. At the same time, it causes the increase in the length of the balloon. Both the dimensions are changing. The radius is changing. At the same time, the length is changing. Now, if you the same is the case with the cylindrical pressure vessels, or for that purpose, the spherical pressure vessels. Both these pressure vessels under the influence of the pressurized fluid, their length tends to increase, their radius also tends to increase. Both the things tend to increase. Now, as far as the increase is of length is concerned, as far as the increase of length is concerned, the increase of length, if you look at the entire material of this pressure vessel, the entire material of this pressure vessel is under the influence of the longitudinal stress, the axial stress. The axial stress which tries to cause the enhance, which actually, so the pressurized fluid will try to cause the change in the length of the pressure vessel. So if you take any material out, if you take any element out, like this element has been extracted out here, this element has been highlighted here, this element will try to oppose the influence of the internal pressure to cause an increase in the length. Okay, so it means in the longitudinal direction, the stresses are generated in this pressure vessel, and those pressures and those stresses generated, we call them as the longitudinal stresses. Apart from the longitudinal stresses, the internal pressure also tends to cause, they also tends to produce the increase in the radius. As the increase in the radius is happening, so it means if you take any surface out, if you take any surface out as has been done here, if you take any surface out here like this one, this section has been drawn, a section has been drawn, and this portion has been extruded out. Okay, this portion has been removed. This is the section that has been taken. So internal pressure is tending to move this element in this direction. It's trying to move it in this direction. So what is happening at this end, at this very surface, and at this surface, lower surface, and the top surface, this section is in contact with another portion of the same section. Okay, so it's like this. It is having continuity. There is continuity between the two sections. It is, that is, this section is in continuity with this section. Okay, so you have a same is the case here. Okay, so it's actually a single surface. It's actually, this is a complete circle. When you take a section out, so you are taking only a portion out at this section, and at this area and this area, this portion is in contact with a similar type of portion. Okay, you have one more portion which is similar to this portion, where at this very area these two portions are in contact with each other. So what the increase in radius is trying to do, the internal pressure is trying to cause the enhancement or increase in the radius. So at the surfaces of contact, this surface will be trying to pull the opposite surface in this direction. Okay, so opposite surface will try to exert the opposite pressure, opposite force in this direction. Okay, same is the case here. This surface is trying to move its counter surface in this direction. That surface, the opposite surface, will be exerting an opposite force in this direction. Okay, so the opposite forces are in this direction here and this direction here. The opposite force per unit of this area is what we call as the stress. So the stress is generated in response to the internal pressure tending to cause an increase in the radius. So when we did the force balance, from the force balance, we got sigma 1 is equal to PR by T. We got this formula. And we said this is what we call as the hoop stress or the circumferential stress. So the value of the circumferential stress or hoop stress is equal to internal pressure multiplied by the radius of the thin-walled cylindrical pressure vessel divided by the thickness. Okay, so this is what we call as the hoop stress. This is what we have done when we did this force balance. Okay, now if we take another type of pressure vessel, okay, apart from obtaining this hoop stress or circumferential stress, we also obtained the expression for the longitudinal stress, which is trying to cause the increase in the length of the machine element. Now the internal pressure is being exerted over this thickness, over this area, which is equal to the 2 pi r into T. Okay, the internal pressure, as far as the internal pressure is concerned, internal pressure is, if you take the projected area of the internal pressure, that is pi r square. On this internal area, the fluid pressure is constant, that is P. Therefore the force by which the internal pressure will be tending to move this drum, will be trying to move the cylindrical pressure vessel longitudinally, will be equal to pi r square into P. But that will be resisted. This influence, P into pi r square, will be this P. Okay, this P into pi r square is the force. P into pi r square is the force which is exerted by the fluid having pressure P, and this force is being exerted longitudinally. Okay, so this force will try to move this section in this direction. Okay, that's why this force has been shown as negative. Now the influence of these forces will be opposed by the portion of the material, since this portion of the material is in contact with its symmetrical portion on the other side. Okay, so there is a symmetrical portion with which this portion and this portion, they are in contact with each other, and the contact happens at this interface. Okay, at this interface, the area of this interface is 2 pi r, that is the circumference, multiplied by thickness, that is 2 pi r and T. At this very surface will be having what you call as the stress, and the stress is longitudinal stress sigma 2. Once we did this force balance, we found sigma 2 is equal to PR by 2T. Now it means it's an indication to us that as far as the stresses are concerned, as far as the cylindrical pressure vessels are concerned, in a cylindrical pressure vessels, we have two types of stress. We have sigma 1 stress, which we call as the circumferential stress or the longitudinal circumferential stress, and at the same time we have another type of stress, what we call as a longitudinal stress. Now apart from these two stresses, if we now start doing our analysis uh, and start working on the spherical pressure vessel and see what we understand by the spherical pressure vessel. Before we understand the spherical pressure vessel, if you look at the corner of your book, there is a cylindrical pipe, cylindrical pressure vessel has been shown, and this cylindrical pressure vessel has undergone a rupture. Okay, there is a rupture is there, that is the breakage of the material has taken place. Okay, it says, it writes at the bottom, this thin walled pipe was subjected to an excessive gas pressure that caused it to rupture in the circumferential or hoop direction. Okay, the stress in the direction is twice than in the actual direction. So this type of failures we often see in the pipelines, in the pipes which are used for transportation of the gas. So you see the type of rupture here. The type of rupture is that is initially this portion of the material was in contact with this. This point was in contact with this. This point was in contact with this. This point was in contact. So the contact between the portions was along this portion. This contact was circumferential contact. It was along the circumference of this pipe. Okay, so when the rupture has taken place, when the rupture has happened, for example, look at this, when the rupture has happened, it means the stress along the circumference was so high that it exceeded the maximum stress along the circumference than this pipe material could withstand. As a result, the rupture happened. Okay, so this type of failure is when you have excessive gas pressure, when the hoop stress is greater than the stress then this material can withstand, that is sigma is equal to PR by T. When you have hoop stresses, when hoop stresses exceed the maximum stress that this material can withstand, then this type of rupture happens. So these types of ruptures do happen when the gas pressures are very, very excessive. Now we have another type of pressure vessel, what we call as a spherical pressure vessel. The spherical pressure vessels, if you look, the spherical pressure vessels are spherical in shape. Okay, they are often used for storage of water. You might have seen spherical pressure vessels in your localities for the storage of water in the form of water tanks. Now again, what will, if this, like you have a cricket ball, okay, and the ball is filled with a pressurized fluid. what will the pressurized fluid tend to do? Okay, the pressurized fluid, at least we can say, it will try to increase the length. It will try to increase the overall radius of this sphere. Okay, like you have a football, you fill the football with uh, pressurized air. Once you are filling your football with air, the radius of the football increases. Okay, now let's suppose we have a spherical pressure vessel, or say for example we have a football, and this football is inflated with air whose pressure is, say for example, P. At the center of this, at the center, you select your coordinate system. Let's suppose this is our x-axis, this is y-axis, and this is z-axis. In case of a sphere, all the three axes are symmetrical to one another, so you can you can treat this to your x-axis, this as y, this as z. This is quite obvious that all the three axes are symmetrical to one another. Okay, if you are moving along x-axis, you are essentially moving along the radius of the sphere. If you are moving along y-axis, you are again moving along the radius of the sphere. If we move along the z-axis, again we are moving along the radius of this sphere. Now the question is, let's again select a small element, okay, as we did in case of a cylindrical pressure vessel. Now look at this element, as look what type of forces this element will be subjected to. Okay, now if you select an element on this surface, on the surface of this spherical pressure vessel, this element, and you fill this sphere with air, then what will happen, that this element will undergo deformation. That is, this element will also, the dimensions of this element will change along this axis, along this direction, as well as along this direction. Okay, this element will move in, this element will, the dimensions of this element will change in the direction as sigma 2 has been drawn, and as far as in this direction where sigma 2 has again been drawn. That is, the element will, if you fill it with, like you have those hexagons drawn on the surface of a football. Okay, once you fill them with air, they symmetrically move in all the directions. They symmetrically, you see the hexagons, all the sides of the hexagon increase in length, but the increase in length is symmetrical. Okay, now if you select, if you don't have an hexagonal element, if you have a, say for example, a cubical element, okay, then this cubical element will change in its dimensions. It will move, its dimensions will change in all the directions. I mean to say, if you are selecting two directions, like you select one direction parallel to z-axis, another direction parallel to y-axis, then its dimension along y-axis will change, its dimension along z-axis will also change. Since this is a sphere, okay, now in a sphere we have what we call as a symmetry. Okay, symmetry, we mean to say, like in case of a football, if you have a football and you draw a square on a football, and then fill this football with air, okay, then the length of, then the length, this square, the dimensions of the square will change. Okay, but the change will be symmetric to all. Whatever is the change in length here, the same will be the change in length here, same change in length, same change in length will be here. So that's why we say whatever. Okay, now you see, as look at this sigma 2. Now this sigma 2 is happening, this is the stress which is generated at this section, at this cross section, at this section. The section plane has been shown here. We have drawn a sectional plane through this sphere. Okay, so it means this portion and this portion are exerting force on each other. Once you are filling this balloon with, once you are filling this sphere with air, fill this sphere with air, so this portion will try to cause motion in this portion, right hand portion will try to cause the motion in the left hand portion in this direction, and in response the left hand portion will try to cause the motion in the right hand portion in this direction. So it means both these portions are exerting force on each other. Now, as far as this sigma 2 is concerned, sigma 2 is the stress which is generated at the interface between this plane, this portion of the section and this portion. So between this portion and this portion, we have the stress that is generated, sigma 2. This sigma 2 is generated in response to the pressure. So pressure is P. Now, if the pressure is P, how much is the force exerted by the pressure? Look at this section. Look at this section. The fluid pressure is P. The force exerted by the fluid, the force exerted by the fluid on this sphere will be equal pressure multiplied by the projected area of the sphere. The projected area of the sphere is the area of a circle, that is pi r square. Pressure into area is equal to force. This is the force exerted by the fluid pressure inside this sphere on this portion, but in this direction, in negative y direction. That's why this is minus. Now what will happen? This sphere will have some thickness. This sphere will have some thickness. The sphere has some thickness. Okay, this sphere has some thickness. Let's suppose the thickness of the sphere is d. Now this portion of the material, this fluid pressure exerts force P into pi r square and tries to move this element, this portion in this direction. But for equilibrium, the force will be, this force is to be balanced. Now look here, the area, the area where this material, this section and this section are in contact with each other, that area will produce the stress that's equal to sigma 2. Okay, and because of sigma 2 the force will be created. That force will try to oppose the force created by the fluid pressure P. Now at this interface, at the interface, at this interface, let's suppose, let me can visualize it. Now this is the interface where these two spheres are in contact with each other. Okay, so the area of this will be, the area of this portion where they are in contact with each other is equal to, this area is equal to 2 pi r circumference multiplied by thickness. And we are saying that at this, in this region the stress is sigma 2, so this will be the force, and this force will try to oppose this force. The force because of pressure is P into pi r square, and the force which is developed by the sigma 2, which is developed by the stress sigma 2 at the interface between the two sections is sigma 2 into 2 pi rt. As long as these two forces balance each other, they will be equilibrium. So we have written the equilibrium equation. So sigma 2 comes out equal to PR by 2t. So as far as sigma 2 equal to PR by 2t is concerned, it means as far as the normal stress is concerned, as far as the stress on this surface is concerned, that is equal to, as far as the stress sigma 2 is concerned along the circumference, it is equal to PR by t. Now in the same way, sigma 2 and sigma 2, this sigma 2 and sigma 2 are symmetric. This is sphere. Okay, it will have a symmetric distribution of pressure in all the directions. Okay, what's this sigma 2 tries to do, the same will be the sigma 2, that same will be the influence of the sigma 2. Okay, so we say the, in all the directions of the sphere the stress generated is sigma 2, and that is equal to PR by Okay, now let's solve this problem. As far as this problem is concerned, it says a cylindrical pressure. Let's try to consolidate on whatever we have done till now, and by understanding this problem. The question is, a cylindrical pressure vessel has an inner diameter of 4 feet. Okay, so as far as the diameter is concerned, the diameter given to us is 4 feet. Okay, and thickness is 1 by 2 inch, that is 0.5 inch. Determine the maximum internal pressure it can sustain so that its circumferential stress nor its longitudinal stress component exceeds 20 ksi, that is 20 kilopascals per square inch. Okay, sorry, 20 kilopounds per square inch. Under the same conditions, what is the maximum internal pressure that a smaller, similar sized spherical vessel can sustain? So we have, this question is composed of two parts. First we will do up to this. So we have been given that we have a cylindrical pressure vessel, and this cylindrical pressure vessel has a diameter of 4 feet. Okay, again 4 feet diameter, and a thickness of 0.5. Determine the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress component can exceed can exceed 20 ksi. So we know, as far as the sigma is concerned, we know sigma is equal to PR by, in case of a cylindrical pressure vessel, sigma is equal to PR by T. Okay, PR by T or PR by 2T. Okay, so when we write sigma is equal to PR by T, at that time the stress that we are writing is equal to the circumferential stress. Let me write the circumferential stress as sigma C, or what you call as hoop stress. And as far as the longitudinal stress is concerned, sigma L is equal to PR by 2T. Okay, and this is longitudinal stress. Okay, now let's see, we are given that neither sigma C nor sigma L should exceed 20 ksi. That is, the value of sigma C is given to us, as well as sigma L, that is, it is uh, 20 ksi, that is 20 kilopascal, sorry, 20 kilopounds per square inch. Ksi means kilopounds per square inch, is equal to what is the P? The value of P we don't know, we have to find it, multiplied by, we are given the radius is given to, the diameter is given to us as 4 feet. Therefore radius will be how many feet? Radius will be 2 feet. But since we are dealing with inch, we have to convert feet into inches. Okay, we know 12 inch is equal to 1 feet. Okay, 12 inch is equal to 1 feet. Okay, so it means when we have 2 feet, that means how many inch? That means 2 into 12 inch. Okay, 2 into 12 inch divided by thickness. The thickness is 1 by 2 inch. 1 by 2 inch. Okay, so we can solve this to obtain the value of P. Okay, so we can do simple calculations to obtain the value of P, and the value of P comes out equal to 417 pound per square inch. Okay, so it is around 417 pound per square inch. This is the value of P. I hope that you can do these calculations to obtain the value of P. So this we have obtained. This has been obtained when we have taken sigma 1 equal PR by T. But we know, as far as the sigma is concerned, sigma is also equal to PR by, sigma is also equal to, this is on the basis of, this we have done on the basis of, this we have done on the basis of what you call as circumferential stress. Sorry, this we have done on circumferential stress. Now, as far as hoop stress is concerned, you know, the longitudinal stress is PR by 2T. So same process you will use. Therefore, this will come out from this formula. The value of P will come out equal to 417 multiplied by, the value of P will come out equal to, from, as we apply the second formula, the value of P will come out equal to twice the value when you apply PR by 2T. PR by 2T is equal to sigma of 20 ksi. Okay, so from this formula you will obtain the value of P will be twice the value of 417. Okay, so P will be 2 times P that you will obtain from this formula. 417 you have obtained already. So when you apply this formula, it will be 2 times, because this will be in the, this 2 will go here. So P will be 417 multiplied by 2. So it means that is equal to 834 pound per square inch. So it means that this cylindrical pressure vessel can withstand a pressure of 417 pound per square inch, and it will not fail as far as the circumferential stress is concerned. But the same pressure vessel, if it is subjected to a pressure of 434 pound per square inch, it will not fail as far as the longitudinal stress is concerned. But at this pressure, at a pressure of 834 pound per square inch, the failure will happen because it will exceed the pressure than this pressure vessel can withstand as far as the failure from the circumferential or the hoop stress is concerned. So it means that the pressure to which this pressure vessel can be subjected to is only 417 psi. Okay, so if you are giving it a pressure more than 417 psi, then the circumferential stress, the machine element, this pressure vessel will fail because of exceed in its cylindrical, because of exceed in its circumferential stress. Okay.
Yes, sir.
See, the second portion is that we have to find the pressure in the pressure that a spherical pressure vessel can withstand. We know in a spherical pressure vessel, the stresses that are generated is equal to PR by 2T. Okay. So we know the value of sigma 20 ksi, we know the value of r, we know the value of t, so we can find the value of p. So the value of p will be 2 times the value of p that we obtained for this cylindrical pressure vessel. Okay, it means the cylindrical pressure vessel under these conditions can withstand a pressure of 417 pascal. But as far as the spherical pressure vessel is concerned, that will withstand a pressure of 833 pascal, psi. Okay, pound per square inch. It means a spherical pressure vessel can withstand more pressure. A spherical pressure vessel having the same radius as a cylindrical pressure vessel, having the same tendency to withstand the stress, having the same limitation of stress, having the same limitation of maximum stress as that of cylindrical pressure vessel, then the spherical pressure vessel can withstand more pressure, can be subjected to more pressure than a spherical pressure vessel. Okay, so this is what we have obtained from this chapter. We'll go ahead, I think, in the next class.